official start, I guess, of AP Calculus BC, but this unit is still sort of called AB Review / Wrap Up. But I guess here in 2019, we are getting into some definite new stuff. So 1.1, we're going to look at what the fundamental theorem of calculus part 1 is all about, and it's pretty much the connection between integration and differentiation. And if you remember from AB, the fundamental theorem of calculus part 2 says that the integral from a to b of f of x dx is big F of b minus big F of a, where f is the, basically the integral of little f. And this part of the fundamental theorem is also called the integral evaluation theorem. And always, as always, pause the video if you need to, if I'm going too fast, whatever. If I'm not giving you enough time to write it down, just pause the video. But moving on, and there's an exploration that if you're interested in, I can show you, that sort of investigates, part 1 of the fundamental theorem of calculus. But here it is. Let's just cut to the chase. The fundamental theorem of calculus, part 1. If f is continuous on the interval ab, then the function big F of x equals this, the integral from a to x of f of t dt. Then that function has a derivative at every point x in the interval, and the derivative of this, is the derivative of this, which just equals f of x. So it's, I don't know, it's very heavy-handed, I guess, if that's the right way to put it, but essentially it's like saying the derivative of the integral equals the original function. But anyway, once again, pause the video to finish writing that down if you need more time before we move on, but here we go. At the risk of repeating ourselves, it's difficult to overestimate the power of basically that. The derivative of the integral is the original function. And when you're ready, I guess you can keep the video going or unpause the video, and let's see how this pretty much unfolds in like actual example problems. As it happens, it's going to be way, way, way simpler than you might think. So here I go. And this a value right here, just some number. So when it comes to doing like the derivative of the integral from like negative pi to x of cosine of t dt, right? The final answer is just supposed to be f of x, right? And so here's my a value, and it's just needs to be some number, negative pi. And so the final answer to this derivative is cosine of x. And that's it. It's just that simple. The derivative of the integral of some number to x, f of t dt is just going to be equal to f of x. So you're just basically plugging in x into the t. And that's it. Same thing over here. 0 is just some a value, doesn't matter what it is. And the derivative of the integral is just going to be f of x. So the final answer here is just going to be 1 over 1 plus x squared. That's it. That's it. Moving on. So let's start to get a little more complicated. What if we were going from, what if the integral was from 0 to x squared? And we wanted to differentiate this integral, Well, remember that the overall fundamental theorem is written like this, but what if we're going to x squared? Okay, so here we go. The upper limit of integration is not x, but x squared, obviously. This makes y a composite, okay, of, say, like this function, and u equals x squared. So, now we have y as a composite function. And whenever we take the derivative of a composite function, what rule do we apply? The chain rule, of course, when finding the derivative, dy dx. Okay, so we're going to be basically doing the same thing except applying the chain rule, because, derivative and chain rule. And just some kind of technical behind-the-scenes mumbo-jumbo. As you know, like dy dx is equal to dy du times du dx. Okay, a little bit of canceling here. We'll prove that kind of thing. And so you're going to just do, well, du dx is going to be like your chain rule type thing. But, and we're going to do d du of basically this, where that is kind of like u, and, long story short, okay, we're just going to be doing like the cosine of u times du dx. And, again, pause the video if you need to. But even to really cut to the chase, all you're really going to be doing, and I'll backtrack here a second, all you're really doing here is you're still, so here's the bottom line, okay, ready? All this mumbo-jumbo, whatever, here's the bottom line. All you're going to do is you're going to plug x squared in for the t, just like before, just like plug x into the t, plug x into the t. You're still just going to plug in x squared in for the t, but then you just have to tack on the chain rule. You have to tack on the derivative of x squared, which of course is 2x. And so that's the bottom line here. Okay, it really is. That's the bottom line. You just plug in the x squared in for t, but then tack on the derivative of that, inside, so to speak, that other thing, function, x squared. So final answer is this, with the chain rule applied. Now let's see kind of another type of scenario. What do you notice about this? What do you think is different? What do you think is new and weird about this example? Taking the derivative of this integral. Did you notice that we're not going from 5 to x? We're going from x to 5. Now remember, the fundamental theorem is some number as the lower limit and x as the upper limit. So what do you think we're going to have to do here to, react, or how are we going to work this when the starting integral goes from x to 5 and not what we kind of need it to be? How do we flip an integral, basically? How do we flip the limits of integration? Well, we just put a negative out in front. So, this integral is basically the opposite, the negative of this integral. So we're just going to basically flip the integral like we sort of need to, but we're going to need to put a negative out in front. And now we can just proceed 5 to x. We're just going to plug in x into the t's. And not really much of a chain rule here needed. What am I doing here? I'm just dropping the parentheses? Okay, that was earth-shattering. An earth-shattering move there. And whatever. But yeah, the final answer is just going to be negative 3x sine of x. And no real chain rule needed here because it's just x, And so that's what you do in this sort of situation. If you need to flip the integral, just put a negative out in front, man. And that's it. Final plot twist. Final curveball, if you will. What about taking the derivative of this integral from 2x to x squared? What are we going to do here? I mean, this doesn't look to fit the fundamental theorem at all, where it's like some number to x. So what are we going to do here? Any ideas off the top of your head? Any immediate ideas here? How can we make this fit the fundamental theorem of Calculus Part 1? Well, what if we broke this up into two integrals? Now, bear with me here because I'm going to take a lot of liberties here, I believe, just in this first step. Okay, so bear with me here, okay? We're going to break it up into two integrals. We're going to have an integral that goes from 2x to, say, 0. Who cares? Just 0, okay? From 2x to 0. And then another integral that's going to go from 0 to x squared. So from 2x to 0 and then 0 to x squared. That should cover all of like 2x all the way to x squared. You know what I mean? So there's my two integrals. 2x to 0 and then 0 to x squared. Now listen, I like the 0 to x squared. I like the 0 to x squared. But the other integral is going to go from 2x to 0. 2x to 0. So now we're going to be adding these integrals together, but am I not going to want to take the 2x to 0 integral and flip it? Flip it so that it's not 2x to 0, that it's 0 to 2x. So I'm going to do all of that at once, and since we're going to flip it from 0 to 2x, now I'm going to make that integral negative and essentially, do this integral minus this integral. I mean, if you feel like you need to do it a little bit differently to make yourself comfortable, like what I'm saying is, if you want to go from, like if you wanted this integral to go first, 2x to 0, 0 to x squared, you're still going to have to flip this. So if you want to think of this as negative this integral plus this integral, if that's how you literally want to write it, that's fine. But this is how I'm going to do it. I'm going to take like this integral minus this integral. And then from here, it's just, working each integral separately, where here we're going to be plugging in x squared for the t, but then there's going to be a chain rule involved here, won't there be? And then same thing here, we're going to be just plugging in the 2x in for t, but won't there also be like a chain rule here, by tacking on the derivative of 2x over here, and the derivative of x squared over here. And so, yep, plugging in x squared, but tacking on the derivative of x squared, which is 2x. And like I was just saying, plug in the 2x here for t, but then don't we have to tack on the derivative of 2x, which is 2. Thank you very much. And then from here, isn't it just cleaning up a little bit? And yeah. And you think we could do even more cleanup? Wait, wrong button, idiot. What color? What color? Let's go purple. It seems to me like this could be... Oh, no, it can't. No, it can't. I thought these two denominators for a second were the same, and that we could subtract... No, I mean, we could, gosh. Yeah, these fractions do not subtract. These denominators do not match. Man, almost like an optical illusion there for a second. But, I mean, I suppose we could make common denominators, but nah, no thanks. So, yeah, I'm just going to say this is actually is the final answer. Good enough for me. And so, look. That's section 1.1, where I know there was like a lot of technical stuff and definitions and like crazy behind the scenes, stuff, but at the end of the day, if you're just going from some number to x, just plug in x for t, or if this was like the cosine of r dr, then just plug it in for r. If it was the cosine of u du, just plug in the x for, I mean, this doesn't have to be a t. Could be a u, could be an r, could be a p, whatever. But if you're just going from just some number to x, just plug in x for the variable. And if you happen to have something that requires, tacking on the, the chain rule thing, doing the whole chain rule song and dance, then you're just going to plug in x squared in for, say, t, but then tack on the chain rule, right? And if you are in this situation, the regular number constant needs to be the lower limit. So if you need to flip your integral, just put a negative way out in front. And if you find yourself in this situation, you're going to break it up into two integrals, with 0 probably being, maybe our go-to a value, 2x to 0 plus 0 to x squared. But you're going to need to flip this one, so you might as well just think of it as this integral minus this integral, right? Since you're going to be flipping and putting a negative out in front of this one. So, and just that's it. That's all the curveballs that you probably have to worry about with the fundamental theorem of calculus, part 1. That's it.